Hello everybody, welcome back. We're still talking about algorithms to compute Fibonacci numbers. And in this lecture, we're going to see how to actually compute them reasonably efficiently. So, as you'll recall, the Fibonacci numbers was the sequence, 0, then 1, then a bunch of elements, each of which was the sum of the previous two. We had a very nice algorithm for them last time, which unfortunately was very, very slow, even to compute the 100th Fibonacci number, say. So we'd like to do better, and maybe you need some idea for this new algorithm. And one way to think about it is, what do you do when you compute them by hand? And in particular, suppose we want to write down a list of all the Fibonacci numbers. Well, there's sort of an obvious way to do this. You start off by writing 0 and 1, because those are the first two. The next one is going to be 0 plus 1, which is 1. The next one is 1 plus 1, which is 2. And 1 plus 2, which is 3, and 2 plus 3, which is 5. And at each step, all I need to do is look at the last two elements of the list and add them together. So 3 and 5 are the last two, I add them together, and I get 8. And this way, since I have all of the previous numbers written down, I don't need to do these recursive calls that I was making in the last lecture that were really slowing us down. So let's see how this algorithm works. So what I need to do is I need to create an array in order to store all the numbers in this list that I'm writing down. The 0th element of the array gets set to 0. The first element gets set to 1. That's to set our initial conditions. Then as I runs from 2 to n, we need to set the ith element to be the sum of the I minus first and I minus second elements. That correctly computes the ith Fibonacci number. Then at the end of the day, once I've filled out the entire list, I'm going to return the last element, f of n. So now we can say this is another algorithm. It should work just as well. But how fast is it? Well, how many lines of code do we use? There are 3 lines of code at the beginning, and there's a return statement at the end. So that's 4 lines of code. Next up, we have this for statement that we run through n minus 1 times. And each time we have to execute 2 lines of code. So adding everything together, we find out that t of n is something like 2n plus 2. So if we wanted to run this program on input n equals 100, it would take us about 202 lines of code to run. And 202 is actually a pretty small number, even on a very modest computer these days. So essentially, this thing is going to be trivial to compute the 100th or the 1000th or the 10,000th Fibonacci number on any reasonable computer. And this is much better than the results that we were seeing in the last lecture. So in summary, what we've done in this last few lectures, we've talked about the Fibonacci numbers, we've introduced them. We've come up with this naive algorithm, this very simple algorithm that goes directly from the definition, that unfortunately takes thousands of years, even on very small examples, to finish. On the other hand, the algorithm we just saw is much better. It's incredibly fast, even on fairly large inputs, and it works quite well in practice. And so the moral of the story, the thing to really keep in mind, is that in this case and in many, many others, the right algorithm makes all the difference in the world. It's the difference between an algorithm that will never finish in your entire lifetime and one that finishes in the blink of an eye. And so that's the story with Fibonacci numbers. Next lecture, we're going to talk about a very similar story that comes with computing greatest common divisors. So I hope you come back for that. Until then, farewell.